right, so I think we are ready to get started. So welcome everyone to day 2 of the AMS Short Course. We're so excited to see you all. So we have a few announcements before we get started. One, we just wanted to say that Slack is down. So what we have moved on to is relying more on Discord, and Michelle has added a whole bunch of different channels into Discord where you can access some of the Python materials that were in Slack earlier, and also just ask for technical help or build community sessions and organize community sessions there. I'm sorry. Okay, so go ahead and use Discord. And like I said, the link is in the chat now. And then the other thing we just wanted to say is for those of you who have received emails to join the small group discussions, if you know you can't attend, if you could email us at that Complex Systems Short Course Gmail, that would be great, because then we can give your spot to someone on the wait list. We also wanted to point out that there have been several sessions organized in the Excel or the Google spreadsheet that I put in the chat window. So we encourage you to go to those as well. And just to note, in that Google spreadsheet, there are actually 2 pages. So if you look at the bottom, you'll see that there are 2 pages worth of different types of meetings that you can go to. And then the final thing is today for Heather's talk, just like yesterday, we'll be looking for questions in the chat. You can put them into the chat window at any time during the talk, and then we will have some brief pauses in the middle of her talk for short questions, but then hold the others for the end. So with that, Heather, if you want to go ahead and share your screen. So I am really delighted to introduce my co-organizer, collaborator, and friend, Dr. Heather Jin Brooks, who is an assistant professor at Harvey Mudd College and is going to tell us all about networks in social systems today. So go for it, Heather.
Thanks so much for the introduction, Al, and thank you all so much for being here. I am so excited to be giving this talk and to be sharing this exciting new style of short course with you all. So I want to start right away from the beginning. Oh, 1 second. There we go. I want to start right away by expressing my gratitudes. I think it's so important, and we always throw it at the end of the talk. So I want to right away acknowledge the AMS for being so supportive of us all putting on this short course together, of Harvey Mudd College and my colleagues there for also being really supportive of all of my work, my amazing co-organizers, speakers, panelists that are making it all happen. And for being able to give this networks talk, I have to acknowledge the 2 mentors in my life who sort of were the first people that introduced me to networks and taught me at least many of the things I know, and that's Nina Pfefferman and Mason Porter. So I have to give a shout out to them. And the biggest acknowledgement of the day is to all of you for dedicating and sharing your time with us, for being here. And that's really like special and wonderful for us to have all of you here to share this with. So I really appreciate it, especially because this has been a really difficult year for so many of us. And it feels really strange to me, I think, to not acknowledge what a difficult year it's been. And so that's where I wanted to start, is to think back on all of these big news stories that we had in the 2020. So big things that were coming up in the news, top of mind, of course, epidemiology, a huge news story. We've been thinking a lot, especially the way that now policy and official messaging is communicated, information on social media and misinformation on social media is currently always a top of mind problem. We had an election year, so we thought a lot about voting and decision making. We had a census year, so we've been thinking a lot about allocations of votes and potentially gerrymandering. And more, thankfully, issues of social justice and racial justice and the ways that people are relating to each other are becoming really prominent issues and are really to the forefront of all our minds. So with all of this crazy stuff going on, you might sort of think, well, what can I do as a mathematician? And of course, there's many things to do, but one thing from my perspective is when I look at this list of issues, I think, well, this makes me realize that understanding connections among people and connections among different social entities is perhaps maybe more important than ever. And that's maybe a guiding principle that underlies all of these big problems that we're facing and thinking about in 2020. And with that start, this leads me naturally into what I'm going to talk about today, which is the study of networks. And to me, I think the study of networks is essentially the study of connectivity. And specifically today, we're going to talk about social networks. So we're going to think about connectivity in social relationships or social entities. And so networks are essentially a formal way to encode relationships among different entities. And then once we have that formal encoding, we can study the structure and implications of those relationships and hopefully get some insight there. So what is a network? I showed some pictures here of things that maybe might be networks, but let's give a few examples to inspire us. So 3 real social networks that I'll start with. So when you hear social network, maybe the first thing you might think of is something like interpersonal relationships. So on the upper left, I have a picture. This is a very famous network called the Zachary Karate Club. And each of those little circles represents a person that's in a karate club. And the lines between them is representing who hangs out together outside of the karate club. So that's sort of friendships and interpersonal relationships in real life. But of course, that's not the only type of social network we could study. We could think about online connections and interactions. So on the lower left, I have a picture of a Facebook friendship network back when Facebook was still just a college network. And of course, we don't have to limit ourselves in social networks to the human realm. We could also think about animal social networks. On the right, I have this really beautiful, complicated flow chart of the different types of relationships that the penguins have at the Kyoto Aquarium, which is one of my personal favorite networks. So 3 examples of ways that we could be connecting socially and thinking about them as networks. Okay, so if we have a network, what kind of questions could we ask about it? If, as a person who studies networks, this is sort of my perspective on what types of things we might be interested in. So one thing you could ask is, what types of structures are likely to emerge in networks? And in particular, are there structures that emerge especially in social systems? If we can identify these structures, how can we interpret them, right? What do they mean? Why do those particular structures emerge? And if we have additional properties in the network, structure or otherwise, how does this affect behavior and dynamics of social systems? So how can we take that information and understand how it might be impacting, the broader system? So a lot of big picture questions that we could be asking. And of course, I'm not going to answer all of these questions today. These are more guiding principles. Here's my goals for the talk. This is sort of a boring slide. I apologize for that. It's boring, but it's full of content. So here's the things that we want to do today. My main goal is to focus on introducing you to some key mathematical tools that we use in the study of social networks. And so primarily that will be tools that we use to measure different properties of networks. And then along the way, I'm also going to introduce you to some popular generative models of networks, and we can use those to dig a little deeper and understand perhaps where these properties come from or why we see certain structures. And also along the way, as we look at these properties, I will in particular highlight specific ways that these show up in real social networks, and we'll try to, in some sense, categorize things that are common in social networks and that might make social networks a little bit different from other types of networks. And then finally, I'm hoping that these slides, once they are in your possession, which they will be soon, that you'll be able to go back to these slides and use these as a jumping off point for whichever direction you want to study. So I'm going to do a big whirlwind. It will be quite broad, not very deep, but there's lots of references at the end that you'll be able to dig into. Some of the slides have a lot more text than I might normally put, but that's not because I intend you to absorb it all now, but because I want you to have something you can go back to later. So that's my plan. We're going to dig into a little bit of math of networks and hopefully come away inspired with the ability to see some of these things popping up in our real world and in our data sets. So sound good? All right, let's get started. So we're here as part of the AMS, as many of us are mathematicians. And so it's well and good to have this formalization of networks, but really what I want as a mathematician is a mathematical representation of networks. And for that, we are, for today, going to focus on the mathematical object called the graph. So many of you may be familiar with the graph. On the right, this is a picture of a graph. What it is a set of vertices, or nodes, which are represented by those little dots, and a set of edges. And edges are just pulled from you take pairs of nodes and you connect them, and we represent them with a line. So vertices and edges, those two sets together make our graph. And a particularly convenient way to code graphs is with the adjacency matrix. And that's what you see on the lower right of the screen. So an adjacency matrix is not so tough to put together for a simple undirected graph like this. All I do is I put a 1 if the edge is in my graph and a 0 otherwise. So I can see that nodes 1 and 2 are connected in my picture. So I might have, or I would have, in fact, in row 1, column 2, a 1 to represent that edge. And similarly, in the opposite of whatever one I said, row 2, column 1, we also would have a 1. So that's our most straightforward representation of the graph. There are several ways to extend graphs that can be quite useful to think about for social networks. This is, again, kind of a whirlwind. There's a lot more, of course, that I'm not doing here. A very common one that I will mention a few times throughout is the directed graph. So we don't have to require that an edge between 1 and 2 means there's an edge between 2 and 1. We could introduce a direction by putting a little arrow on that edge. And so that's going to, of course, also introduce asymmetry into our adjacency matrix. So that's one thing we can do. We could impose direction in our graphs. We could add self edges or self loops if we're interested in nodes interacting with themselves in some way. We could introduce multi-edges if we wanted to have multiple edges between nodes. And perhaps an extension of this idea of multi-edges is we could actually introduce weights on the edges if we want to represent somehow the strength or the weight or a value of some sort of connection or interaction. So we could put any sort of values we like on those edges. And so here I have an example of now no longer a simple undirected graph, but rather a directed graph, a directed weighted graph with a self edge. And there's our corresponding adjacency matrix. Okay, so now we are going to dive in. This is the main part of the talk, and it's going to be a big whirlwind of network properties and generative models. So I'm going to give you a little bit of a taste of different properties we can study now that we have these mathematical objects to represent networks with. So I'm going to start with one that you may have seen before, if you've seen graphs or networks before, and that is the idea of degree. And so the first natural question, at least I think I would have, is like, how many contacts or interactions or connections does an individual node have? And that's exactly what the degree measures. And so we can find degree by summing over here. Summing over the columns is usually the way we could do it. If we have an undirected network, we can sum columns or rows. It's symmetric, we'll get the same thing. If we have a directed network, we want to distinguish between in degree and out degree. How you define these does depend on how you've defined your adjacency matrix, but here's the way that I will define them. Summing over the columns will give us the in degree, and summing over the rows will give us the out degree, if I'm going to match the way that I defined my adjacency matrix earlier. All right, so here I have a picture of, I think one of the best examples of in degree and out degree is to think about Twitter. So if you imagine Twitter as a network, you could think about accounts as nodes, and you could think about followerships as edges. So here I have a screen capture of Dionne Warwick's Twitter bio. And this is actually, I made these slides a couple of weeks ago. So this is outdated followership data here. She has many more followers now, I think. But her number of followers, we could represent those as in edges, arrows pointing to her. And she has over 330,000 followers. So that would be her in degree. And then she's following over 4,800 others. So that would be her out degree. Okay, so that's degree. And another thing we might wonder about is, well, it's very well and good to know how many connections you have, but like could we get between one node and another, right? How could we sort of traverse these connections? And really, you could think about this as like, and I do think about this as walking along a graph, and we call it a walk. A walk is just mathematically a sequence of edges that connects a sequence of nodes. And a path, you'll maybe more likely in the literature hear this word path. And a path is just a walk that does not intersect itself. So you don't go through the same node more than once, and you don't traverse the same edge more than once. And so here I have a picture of a little graph, and then highlighted in blue is a path. We could start at 1, hop to 2, hop to 3, hop to 5, and that will be a path of length 3 from node 1 to 5. So there's a way to traverse the edges and get between 1 and 5. And an interesting, fun little mathematical fact is you can find the number of walks of length r between two nodes by taking the matrix A to the r power and then looking at the ijth component. That's what this notation I'm using here means, is the ijth component of A to the r, the adjacency matrix A to the r. And this is actually a really great technique for finding cycles. If you want to prove this to yourself, it's not so bad. It's a nice little induction proof to show that this is the number of walks. And once we have this idea of walks and paths, ways to traverse between nodes, we could start talking about components. And so you'll see on the top this sort of wordy definition or wordy explanation of what a component is. But I think actually it's pretty intuitive. It's sort of what I think it sounds like it should be. If I can take a sequence of edges, if I could take a walk between one node and another, they're in the same component. And the second part says we can't add other nodes and still preserve this property. That's so what we have is sort of, we have the minimum number of nodes that we would need to have that component. And if all the nodes in a network are in the same component, we say it's connected. So I have 3 examples here for you. The one on the right is all the nodes. There's a path between every node and every other node. So that is a connected network. The middle picture, we have 2 components. So hopefully you can see those there. There's no way to get between those right 2 and those left 3. And then this might surprise you, but the network on the left with no edges, that has 5 components. So a node by itself can be its own component. And I have on the bottom another definition of components that may resonate more with some of you, which is you could also think about components as distinct maximal connected subgraphs. So if that means something to you, maybe that's a nice way for you to think about components. And okay, this is a bit of a technical slide, but I have to talk about, I can't give a talk on networks without talking about the Graph Laplacian, which is essentially, this might seem like I'm going off in a different direction, but the Graph Laplacian is actually a convenient way for us to understand mathematically how many components a network has. And you can see at the top, I've written down a definition. And this is another way you could represent the graph. So what you could do is take your graph and create a diagonal matrix where the degree of each node is along your diagonal, and then subtract off the adjacency matrix. Great, I can do that. But you might say, Heather, why would I do that? That sounds ridiculous. It turns out it's got these amazing properties, in particular these amazing spectral properties, which are so useful. And a lot of them are not too tough to show. So this is, if you haven't seen this before, it might be worth thinking about where some of these properties come from. So the first place I'll start is that you can show pretty easily that all the eigenvalues of L are non-negative, and the smallest one is always 0. So we always get at least one 0 eigenvalue. The second smallest one, it has a special name. We call it either the algebraic connectivity or the Fiedler value or the Fiedler eigenvalue. And I'm going to sort of sweep under the rug what I mean by this, but it in some sense reflects how well connected the overall graph is. It has relationships to spreading diffusion processes. It can also be used to partition, the eigenvector that's associated with it can also be used to partition the network. So some cool properties in that second smallest eigenvalue that could be 0 as well. We could have more than one 0 eigenvalue. The Fiedler eigenvalue could be 0. The smallest, if you get past all the zeros, the smallest non-zero eigenvalue is the spectral gap. And so that actually gives you some interesting properties as well. And most importantly, for what I'm talking about right now, by looking at the spectrum of L, by looking at that set of eigenvalues, we can actually see how many components the network has. And this proof is not so bad. And I can point you to some resources if you're interested. But here's the big statement. The number of 0 eigenvalues that our Graph Laplacian has is the same as the number of components our network has. So let's look at this little example that I have on the right. I have a network we now know has 2 components. And I've written the Graph Laplacian down. And oh, it's so interesting, right? It has this beautiful, or at least the way that I've numbered the nodes, it has this beautiful block structure. And the eigenvalues are on the bottom there. That's the set of eigenvalues. We have 0, 0, 2, 3, 3. 2 zeros, 2 components. It's beautiful. All right, so that gives us actually a really nice, quick way we could use a computer or some sort of mathematical software to very quickly see how many components our graph has without doing too much work. So that's good news for us. Okay, so back to components. Let's talk about components in real networks. And this is actually true not just in social networks, but in many types of networks. But social networks in particular, one property, first big property we're seeing of them, is that they often contain a large component. This is not totally obvious why this should be true, but we see it again and again. Now, this example that I put up here is actually probably not the best. There are much more striking examples of large components in social networks. But I just really like this example, so I put it on. What you can see here is each little node represents one of the penguins in the Kyoto Aquarium example that I talked about earlier. And the edges here represents heartbreaks or breakups that they've had. So the penguin relationships are really fraught and difficult. And so every time you see a directed edge, that means that penguin broke the other penguin's heart. And you might think, I don't know, initially I would think that maybe we would just see like a bunch of small little components, but we see that there's one component that is where many of the nodes are connected together. So it's like kind of a surprising example, I think, of the large component, the penguin heartbreak network. But this shows up all over the place. It shows up on IMDb networks, it shows up on social media networks, and on and on. So, okay, can we understand, like, why does this happen? To understand this, I'm going to introduce our first generative model. And so generative models are mathematical models where we think about a way to construct a graph, and then we could actually really dig in and do some analysis. So we could essentially construct a whole family of graphs that satisfy some sort of properties, and we can study them. That's the idea of a generative model. And the first one I'm going to introduce to you is called GNP, or Erdős-Rényi models. And the idea of GNP is not too complicated. So you're seeing a mathematical definition, but I think the intuition is not so bad. So the idea is that you choose your number of nodes, that's n, and then you choose the probability that an edge appears between any 2 pairs of nodes, that's p. And so mathematically, the way that it's really convenient to think about this is that GNP, you select the n, you select the p, then what you have is an ensemble of simple networks where each particular graph appears with the probability that I've written down here, right? So, and m is the number of edges. So it's really like an ensemble of things that you could get with a particular n and a particular p, and what is the probability that that graph appears. So here I have 4 examples. If I've set n to be 5 and p to be 2/5, you could ask yourself, okay, which of these is maybe the most likely to appear? Each of these graphs would appear with some probability. And you could think about it and test your intuition, and then I'll show you here. If you calculate it, here's the probability that each of these graphs would occur, which I don't want to project. It may or may not match your intuition. So if it doesn't match your intuition, think about why. If it does, you have awesome intuition. Okay, so that's the idea of the GNP graph. Super simple to construct. They're pretty simple to understand, I think. and they're quite useful for analysis as well. There's a related class of models, which I won't talk about too much, but they're called Gnm models, where instead of fixing the probability of an edge appearing between two nodes, you could just fix the number of edges. Those are usually called Gnm models. So related, but not actually the same. It's important to distinguish when you're creating your own network models. All right, and being able to write down these probabilities with GNP means that we could start to get some intuition behind the large component. So I'm skipping all of the details here, although if you're interested, let me know. I can give you some notes that I have on this calculation, but I'm just going to give you a really brief sketch of the intuition behind why you often see a large component appearing in GNP models. And so if we take this little bracket K to be the mean degree, then we can show by writing down some probabilities and thinking through a couple of things that the average fraction of nodes that belongs to a giant component, if we call that S, it's after a little bit of approximation, that's equal to 1 minus e to the, up in the exponent, we have the mean degree and S again. This is not so easy to find a closed form solution to, unfortunately. But if you're clever, you could do what I've done on the left here and try to draw the intersection of the left hand and the right hand side. So you have the green line being just the one-to-one line, y equals s, and the purple lines are the right-hand side for different values of mean degree. And what you might notice if you do this is that at some point, as your mean degree gets larger, all of a sudden we realize we have two intersections. That means we have two solutions. And in fact, the place where this happens is mean degree equals 1 is the transition point between these two. So I could plot that on the right-hand plot shows this. In green, what I'm plotting is the fraction of nodes that we expect to see in our largest component or a giant component. And what happens is we expect to see no giant components if we have a very small degree. And then all of a sudden, when we hit mean degree 1, we expect to see a larger and larger fraction of nodes in that biggest component. And if you think about it for a minute, this makes sense because we would expect like the more connections you have, the more likely your graph is to be connected. So maybe actually the intuition is pretty reasonable there. Again, I've skipped a lot of details, but I'm happy to share those if people are interested. Okay, we are at our first question break. I'm ready to take a few.
Okay, thanks so much, Heather. So I think there are a lot of people who are interested in seeing some of those notes. So maybe just one question that I'll pass on now. So is related to slide 14. So Eric Rosen was wondering if you could give some intuitive explanation for spectral gaps.
So I like intuitive in the sense of what we would use them for, or is that perhaps?
I think just intuitive in the sense of, so the question was intuitive explanation of spectral gaps, maybe just like what it means or
whatever you're feeling. When I say intuitive, whatever comes to mind for you. I just quick runner of it, but go run with it.
I love, yeah, okay, free association. What do spectral gaps make me feel? So this is something that that comes up a lot when you're thinking about dynamics on networks and you want to think about perhaps how well something might diffuse or spread through a network. That's a place that I would go. But I think there's a lot of ways people use it that's not that. And so if you have something else, that's okay too. That's just what comes to mind for me. So in the example that I have here, the spectral gap would be 2. So that's something that we might want to think about. It only really means something in the context of this particular network, right? But I don't know. Hopefully that sort of gives you an idea. It's telling me something about the connectivity and the structure of the network and how things can traverse around the network. I think I'll leave it for that.
That's great, Heather.
Do you have anything else?
We'll do one other question. So from Andy Miller on slide 17, he was wondering, can you think of GNP as kind of a random variable whose events are graphs?
Yeah, I think that's right. So one graph is a particular realization of this distribution. So exactly, that's yeah, I think thinking about it as a probability distribution is a good way to go.
Great. All right, that's good for now.
Wonderful questions.
Oh, actually, and one other question. P is a parameter here, is the only other question that just came in.
Yes, so N and P are both parameters. So when you're creating your GMP model, you get to choose what these things are. That's right.
All right, we'll hold more questions till later on.
Sounds good. Yeah, thanks for the questions. This looks, you guys are paying attention. This is very exciting. All right, let's get back to where we were and carry on. Okay, so more whirlwind properties. I'm gonna take a step back to where we started, which is I'm gonna revisit degree again. So what we really just did is this whole, we did a whole little traverse about walks and paths and components and things we can do there. So I want to revisit back with degree and what we can learn from degree. And to do that, I want to introduce this idea of centrality measures. And centrality measures are a way that we quantify the relative importance of nodes in a network. So importance, of course, is very, importance depends on your application. That's very subjective. But degree is perhaps the first way we could think about to measure this idea. So we could calculate the degree of every node in our network, and we could put that in a set. We'd call that the degree sequence. Or since we're clever and we know how to write this in terms of adjacency matrices, we know we can just like sum the rows and get an in degree or a degree if you're undirected. And great, there's a quick way to calculate all your degrees, get your degree sequence. Or you could look in that vector, you could call each of those the degree centrality if you're using this to measure importance. So if we revisit our Twitter example with in degree, we could look at in degree as our centrality measure. Maybe I would think that someone that has more followers is more important. So with that metric, Dionne Warwick with her over 330,000 followers, it appears to be more influential on Twitter than the AMS, which has 52,000 followers, and both are much, much more influential than me, who has 1,000 followers. And I just found out last night, I was talking to my mom about this, and she's like, oh, I think I follow you on Twitter. And it turns out, no, my mom doesn't even follow me on Twitter. So she is not one of those 1,018 followers. Very funny. So anyway, degree, one way to think about importance. That's like it's quite a useful notion, quite a useful way to think about nodes in your graph, but it's, we might want to think about ways to extend this, or there could be some ways that this fails our intuition a little bit, because maybe somehow I just get followed by like a lot of bots, like then maybe I'm not so important, right? And so one thing we could do, these are just, this is a real quick and dirty slide of some popular extensions of centrality that are similar to degree centrality. So one thing you could do is to say, okay, maybe the importance of a node itself should be proportional to the weighted sum of the importance of all its neighbors. So if it's connected to a lot of other important nodes, it must be an important node. If we write that down, we realize, oh, this is actually just calculating the eigenvector. And so we call that eigenvector centrality. So that's one extension you could do that's a degree-based centrality. There are some problems with this, in particular in directed networks. You can have some funny situations where you end up with nodes with 0 centralities that really you might think intuitively should not have 0 centralities. And so CAT centrality is one way to address this. And you do this by essentially giving every node some centrality for free, adding a constant term to your centrality equation there. And then a further generalization of this is Pagerank centrality. And there's sort of two ways to think about it. One is to start with CAT centrality, but then normalize your in edges by your number of out edges. So maybe if I also follow a lot of other people, maybe I'm not so important. Another way to think about Pagerank centrality is that we could think about it as what happens, or this really the stationary distribution of a random walker on our network. So you could, if you're walking around on a network, how likely are you to visit any particular node? And that's actually captured with the Pagerank Centrality. So you can see some mathematical details here along the bottom, but hopefully that gives you just a general flavor of ways you could use degree or degree-like objects to rank importance of your nodes. Okay, so I want to actually dig in talking even more about degree specifically, though. And the thing I want to talk about is, what do degree distributions look like in social networks? So if I take my degree sequence, or I take maybe a normalized version of the degree sequence, we could get what's called a degree distribution, or we could create a degree histogram. What does this look like in real networks? And it turns out that very often social networks can be heavy-tailed. And what I mean by that is that there are a small number of nodes that have a very large degree, and a large number of nodes that have quite a small degree. And so you see three examples from the literature here of this. The one on the left is Facebook friendship data from 2011. The one in the middle is the number of times an account was retweeted in a Twitter dataset. So retweets also having in this particular dataset a heavy-tailed degree distribution, and number of collaborators in a co-authorship network of math papers. Oh, and what I should have mentioned this at the beginning, apologies. Along the horizontal axis of all three of these, you'll notice these are log scale. So this really is truly like heavy-tailed distributions in all three of these cases. So let's revisit our good old friend, the GNP model. And now that we have this nice mathematical formalization, we could think about what the degree distribution of this is. In fact, we could calculate it exactly. It's not so bad. I remember that probability P is my probability of being connected, or the connection between any two nodes. And so I could write down the probability of being connected to K other nodes. And oh, hey, this just gives me a binomial degree distribution. And so I have here two examples where I've chosen N. On the left is 100, on the right is 500, and I've chosen P to be 0.02. And the insets are the particular realization of the network, and then you see the degree histogram. And this does not look like the histograms that I showed you on the previous page, right? This sort of has a lot of, the most nodes have sort of this, middling, middle degree, not a particularly large or particularly small degree as compared to the other nodes. And so maybe we might want to think about constructing generative models that could capture the property of degree distributions that we see in real social networks. And that was the idea, that brings us to the idea of preferential attachment. So this was first started by a person called Price, who was studying citation networks. These were sort of the directed version is due to Price, and then later is popularized by Barabashi and Albert. And here's the idea. What I could do is I could construct a network by starting with some number of nodes, and then adding a new node or a new set of nodes every time. And as I add those new nodes, I get to define the probability of connecting to any particular already existing node. And if we define that probability to be proportional to the degree of the nodes, we get something called preferential attachment. And so the nodes with high degree, they're more likely to gain new edges in this context. This is you might think about it as a rich get richer model. So this makes sense for something like citation networks, because a paper with high citation count would be perhaps more likely to be found, and perhaps also more likely to be cited again. And so what you find when you study a model with preferential attachment, as Barabashi and Albert did, you'll notice that, or you can show that these models have a degree distribution that satisfies a power law. And that's what you see on the left. This is so a heavy-tailed distribution, sort of like what we see in the real networks. And often in the networks community, if a degree distribution satisfies a power law, they're sometimes called scale-free. So Mason alluded in his talk yesterday to power laws and dramas about power laws. And I've decided to skip that for this talk. I mean, that's a whole talk in itself. There's big debates about, are real networks often scale free? Do they satisfy power laws? What properties do they really have? And so I'm just going to provide you some links to read for yourself and see what you think about that. Yeah, it's a very spicy debate in the networks community, actually. So this is one nice model that would give us a sort of distributions that we saw in those real networks, but we could even maybe go a step further and say, well, actually, I just want to make a model that has like any degree distribution I want. And configuration models are a class of models that allow us to do that. So there are a couple of ways to think about configuration models. One would be to essentially just fix the degree distribution that you want. And then with that, you know that you have some probability of getting a particular degree sequence. And then you have a probability for getting a particular graph with that sequence, given that you fixed the distribution. That's essentially the idea of the configuration model. So this is very nice because, especially for analysis, when you want to study some properties about degrees, if you fix the degree distribution, well, then we can rely on the information that we know about distributions, right? We can use things like probability generating functions, and it's a very powerful analytic tool. So this is a way to construct some null models that have degree distributions, any degree distribution that you like. Okay, so that's as much as I will say about degree distributions for today. And now I'm gonna head back over to talk about paths. And I want to talk about how connected two individuals are. So we talked a little bit about, can you get from one to another? How many components do we have? Do we have a large component? But if we think on a more micro scale, like how difficult is it or how easy is it to get between two particular nodes? And to measure this, we use a quantity called the shortest path, which is exactly what it sounds like. It's the length of the shortest path between two nodes. This is sometimes also called the geodesic distance. So here's a little example. You can test your understanding on the length of the shortest path between 3 and 4 here is 2. And then if we want to zoom back out and have some sort of summary statistic for the whole network, a popular one to use is the longest shortest path. So that's if we take the shortest path between all the pairs of nodes and then look for the longest one, we call that the diameter. And so for this network, that's 3. So it's either between 1 and 5 or between 3 and 5. And that tells us something about maybe how far we might have to hop to get to any other node, right? Here, no more than 3. That's what the diameter tells us. And this gets us to a property that you may have heard of when you're thinking about social networks, and that's called the small world effect, which is that the diameter or a different but sort of also interesting quantity, the mean geodesic distance in social networks is often surprisingly small. So you may have heard this in the context of Kevin Bacon or in Stanley Milgram's letter passing experiment. We have many mathematicians here, so I had to shout out Erdős numbers. So you could calculate in the mathematics collaboration network, you can calculate your Erdős number. That's if you've published with someone who's published with Erdős and so on. You can I have a link for you to calculate if you want to know, if you're on MathSciNet. Mine's not very good, as you can see. My favorite example of this is 6 degrees of Wikipedia. This is sort of it's like just for fun, like a game of how many links it takes to connect to Wikipedia pages. And I highly recommend you check out that page. There's some really like amusing short paths between different pages. And we do, as I was suggesting, we see this in social networks like online social media networks like Facebook. The picture I've shown here is from a 2011 paper. And we could do a quick calculation on like why this would make sense for Facebook. So in this example, the median number of Facebook friends at the time that data was collected is 99. So we could approximate this by saying, well, maybe if I have the median number of friends, I have 99 friends, And then, well, my friends, they have me as a friend, but then they have 98 friends, and then their friends have 98 more friends, and we could go on. Well, if we do this within 6 hops, that's a really big number, well within our ability to like capture everyone in the world. So, okay, that makes sense. But I'm sure many of you are like, I don't have the chat open, but I'm sure you're screaming into the chat like, this is terrible, right? This is like not a good approximation, because you think of, what did I miss here? Well, like, you know, a couple of things, but one big thing that might really be getting you is that I've neglected the fact that 2 friends of some people are also often friends with each other. And this is a quantity that's called clustering. And I've given you here, I won't go into the details. You can read through this if you're curious, but I've given you here 2 ways to calculate clustering. So it's essentially looking at if 2 of your friends are also friends with each other, and what proportion of those is that true. You could use that to measure the clustering, or sometimes it's called transitivity of a network. And it turns out that social networks often have this property. They often have a high clustering coefficient, or a high level of transitivity. And so I have brought in our 4th generative model, which is called the Strogatz model. And this is a way to capture clustering while also preserving that small world effect, keeping that mean shortest path to be small. And the idea of this model is that you could start with a ring lattice. So choose your number of nodes, choose your number of neighbors for that node, connect them all in a lattice like you see on the left, and then choose your probability P of rewiring. So go through each edge and change to a different node with probability P. And then what happens as you increase this probability P, of course at 0, you stay with the lattice you started with. And as you increase, what you start to get is little shortcuts. And you can see on the right, what happens is you increase P, is the shortcuts give us a smaller mean shortest path, right? It's easier to get between nodes. But the cool thing about this model is that the clustering actually is still preserved. So we do see clustering like we see in the real social networks. Now, if you go all the way up to P equals 1, you're back to recovering a random graph model. Okay, so when we're thinking about paths, I want to bring back our idea of centrality measures. So we could think about importance maybe in this context. If we realize that short traverses in networks is something that shows up a lot, we could also think about the fact that maybe a node is really important. If we want to measure importance, maybe it's important if it's a short distance from many other nodes, right? If its shortest path between many other nodes is small. We call that measure closeness centrality. And then there's another measure that's path-based, which is called Betweenness centrality, which says, well, maybe a node's important if it lies on the path between many other nodes. So if that node is a connector of many other nodes, maybe that's an important node. We call that betweenness. I have an example for you to explore on the bottom of this. This is a cool example where degree, eigenvector, closeness, and betweenness centrality are all different nodes in the same network. So I think that's something interesting to think about. And a very famous example of this in the study of social networks is the Medici family having a very high betweenness centrality when you do a network of 15th century Florentine marriages. So it's like a fun example where betweenness centrality really seems to give us some interesting information. Okay, let's do a quick question break before we fly through our last section, maybe? Or actually, Alexandra, do you want to just wait till the end since we're
I think that sounds good, Heather. Yep, keep going.
Awesome. So what I have left is a few more. We'll fly through. Again, I have much more information on these slides than I can do in the time here, like in depth. So this will be some things for you to explore later. The final properties that I want to talk about that social networks often have are ideas of assortativity and homophily. So that's the idea of whether like nodes tend to connect to each other, or whether unlike nodes tend to connect to each other. And we see both in social networks. So the example I have here is a romantic relationships network where the nodes are disassortative by gender. And we can calculate this quantity. I won't go into the details now, and that we call that the modularity. That tells us how likely same type nodes or different type nodes are to be connected in a particular network. A particular important type of assortativity is degree assortativity. And social networks often tend to be degree assortative. So don't worry too much about the details on the right. You can dig into those later, but this is a way to think about modularity in terms of degree. And then in the chart, you'll see a bunch of social networks on the top part of the chart, which all have a positive value of degree assortativity, and many other, maybe not, well, I could argue whether internet is a social network or not, but the non-social networks tend to be disassortative by degree. So an interesting property where popular people tend to be friends with popular people. That's what this would say in intuitively. And so why would we, you might start to think about what are the reasons that we might see all this clustering and assortativity in networks. And one theory behind that is that networks often have community structure. And so the idea is that we might have several densely connected subnetworks that are more sparsely connected between them, like this little schematic that you see on the right. Community detection is a huge field, and that's, again, its whole own talk, so I don't give any details here. But I highlight a couple of methods that are commonly in use for community detection in networks. And you'll recognize some of the properties that we've already seen today, like modularity, using the Graph Laplacian and the spectrum of the Graph Laplacian, betweenness for the Gervan-Newman method, and other statistical and minimum cut methods, and many, many others. So I leave that to you to read. Instead, I just want to show you two fun examples. One is that Zachary Karate Club that I introduced at the beginning. So we have essentially two different factions in this karate club, and community detection. This tends to be a benchmark for community detection. Here they've used leading eigenvalues, eigenvector maximization, and they've split into some different communities there. And then on the right, the colors represent different communities. This is a network of co-authorship of some network scientists. And our final generative model is the stochastic block model. We could think about, in some sense, generalizing our configuration models or generalizing our GNP models, and creating block structures for our adjacency matrices where the probabilities are different within groups and between groups. And if we do that, we can get all these different types of interesting structures. So that's a really powerful type of generative model we could use. And I think, so for time, I will probably, because I'd rather get to maybe some questions, I'm just going to fly through. The rest of this is just me highlighting some areas of current research, since I did a lot of foundational mathematics stuff in this talk. So these might be areas for you to explore, and there's lots of references. And so let's fly through. One is time dependent, allowing the edges to change. Multi-layer networks like the Penguin network that I've been highlighting several times. So you could think about different layers of a network, perhaps representing different types of relationships or different temporal realizations of the network, and so on. So a lot of exciting new work coming out of multi-layer networks. Thinking about moving beyond those dyadic interactions to include interactions among more nodes than just two. And that's going to come up a lot tomorrow when we talk about simplicial complexes. But hypergraphs are another big area of study for polyadic interactions. And then the last thing, of course, is dynamics on networks. This is my area. This is where I get really excited. And that's where we could allow node states to change in time and think about studying dynamics on networks. So that would include percolations, contagions like the SIR models we've all seen this year, memes, voter models, consensus dynamics, synchronized oscillators, on and on. This is, again, totally its own talk. So I've not done it justice here, of course, but a really exciting area of study, especially in today's world, I think. And last thing is, of course, you could combine these. You can get things like adaptive networks where they change in time and they're dynamic. Lots of very exciting stuff. So with that, I'm going to conclude. We have done a complete whirlwind of networks. It's really way more than anyone should do in one talk, but here we are, I did it. And what I want to highlight is the properties that we notice that social networks have often, namely large components, heavy tail degree distributions, small world effect or small diameter, high level of clustering, often assortative by degree, and frequently we see a lot of community structure. And then you can see in here some of the tools that we saw, some generative models that we can use to study them. And again, you can now go back and dig into any of these things that, that spark your interest or that feel exciting to you. And there's so much good stuff to do in networks, both in terms of understanding applications and digging into data, but also I think there's a lot of really exciting mathematical advances to be made too. So whatever your bag on that spectrum, I think there's great stuff to do. So I'm going to conclude there. Here's just a preview of how many references I have for you. Check it out. That'll be fun. You can read that later. And I will stop there and take a few questions.
Thanks so much, Heather. So the chat is filling up with people complimenting how lovely the talk was. So we have a whole range of questions. And so I'm going to start kind of broad. So first, I was wondering if you, so actually, Don Natali was wondering if you could comment on ways of dealing with time-varying graphs, or maybe even suggest some references for working with time-varying graphs and networks.
There are references in there. Yep. That was one of the slides I had at the end that I really flew through, was the temporal networks. So yep, there are references in there. And one of the ways that I think has gained a lot of traction is to think about them as multi-layer networks. So for Don, I would also suggest getting into some of that multi-layer networks literature, because thinking about, especially if you have discrete time, this is a really nice way to think about each discrete time step as a layer in your network. So that would be a good part of the literature to dig into as well. So yep, it's in there. Good question.
Great. Okay, and then another question that showed up in various forms in the chat, also from Polly Yu, was basically, can you comment on working with social network data when you're building networks from real data? What form does this come in? Does it come in an adjacency matrix? How do you handle real world data, and what kind of challenges come in that process?
Oh yeah, a lot. So I think that more of this will I think Daryl will probably dig into a bit more of this than I will, as far as like, is there a standardized way that you will get the data? No, unfortunately not, right? You're gonna see data sometimes. If you're lucky, people will report adjacency matrices, but that's not always true. Sometimes you'll get node edge pairs, or sometimes you have to construct it yourself. And that's where those modeling decisions are going to come in. So for all the networks that I showed, there's not like, from above an ordained way of saying what nodes and edges mean in those networks. That's a modeling decision that you have to make. And so that's, if you're scraping real data, sometimes that's something you'll have to think about, and you may have to, construct your own node edge pairs, construct your own adjacency matrices. So yeah, lots of choices, and no, it is not standardized.
Okay, so I think we have time for maybe one more question, but again, people can, I'm sure, reach out to you on Slack if their question didn't get answered. So this is from Irene Ferry. It's a little bit more detailed. She was wondering if there's a relationship between modularity of participants and betweenness centrality.
If there's a relationship between modularity and betweenness?
Betweenness centrality and modularity of partitions.
Yeah, so for Irene, I'm gonna point her into the community structure section. So community detection is the place where this connection happens. And in particular, if you look at, this paper should be one of the ones in the references, Girvan and Newman, Michelle Girvan and Mark Newman have a paper where they really dig into this. So I think that's where I'm going to point you for looking at that connection. But yeah, that's a way we can start thinking about community structure, right? Nodes being alike, and also who is the paths between those alike nodes. So yeah, that's a great observation, Irene.
All right, so I think we will go ahead and stop there. And thanks again, Heather, for a wonderful talk. We'll take
Thank you so much for coming on this whirlwind. There was like a real chaos energy, but we did it. So I appreciate it.
Super. All right, well, we'll see everyone in 30 minutes then for Daryl's part 2 of networks.